Hello, my name is Branden Jackson. Here is my Bearcat card. As you can see, that is me. And I will be going over the final exam in our Statistics 1031 class. So first, we're asked to use the 5-step hypothesis testing process to check the pH group's population average total cholesterol if it's significantly higher than 210 and use alpha equals 5%. And we are given, let's see here, excuse me. We're given our sample mean, which is 214.71, our population variance, which is 879.47. With that 879.47, we can find the standard deviation by finding the square root, which will be 29.66, and we are given a sample size of 133. So for the first step, we do our null and alternative hypothesis. I'm sorry if this is a little quick. I don't have a lot of memory on my phone, and I don't really know how it's going to, if it would even be able to send to my laptop so that I can upload it. So I kind of want to keep it a little brief, but I will hit everything. So for our null and alternative hypotheses, we have our h of O and h of 1 being equal to, or n equals 210 and greater than 210. This is a right-hand two-tailed test because we have the, we have the standard deviation values as well as the population, and so we do the z-test. So our next step, now that we have figured out what our null and alternative hypotheses were, is the rejection region basically, and we have our significance level of alpha equals 5%, which was also a given. So we know that that's 0.05, and using the standard normal table, we can use that 0.05 to find the critical z-value, which we find to be 1.645. Like I said, using the table, you can use technology or the table, but in this case, we use the table. So now we do the test statistics, which equation will be that z is equal to x minus that 210 value we had from the null and alternative hypothesis divided by our standard deviation over the square root of our sample size. So what that would basically equal is z equals 214.7 minus 210 all over 26.66 radical 133, all over radical 133. And we will get a z-score, or a z-value of 1.831. Let's see what we got next here. Okay, now we accept or reject basically this step, our null hypothesis. So the z-value from our equation was 1.831. The z critical value from the table is 1.645. So basically our z value from the equation is greater than our critical z value. And if the z-stat value is greater than the z critical value, we know that there's enough evidence to reject the null hypothesis. So, and by the way, that was part 4 of the first problem. Kind of moving along here. And now for the 5th part, our population mean. Actually, let me make sure I'm reading exactly what it's asking for here. Oh yeah, it was just the 5 steps. Okay. So they don't really ask for specifics. Okay, that's fine. Basically, the population mean is greater than 210 milligrams per. I really don't know what the DL stands for. That's kind of insignificant. One of the significance is 5%. Cool. Question number 2. And like I said, I will attach my actual exam here. I didn't show you guys before, but this is like my whole exam here. And I'll attach this underneath so you guys can kind of follow along a little better, or so you, professor, can follow along. I'm sure nobody else really cares. Okay, question number 2. So, so we're given a pH sample mean of 214.71, a pH population variance of 879.47. We find this by taking our standard deviation and squaring it. Our standard deviation, again, same as last problem, was 29.66. Our pH sample size, or N, is equal to 133. Our NT sample mean is equal to 193.20. Our NT population variance is equal to 1091.96. That is the standard deviation squared. The standard deviation is equal to 33.04. The NT sample size, N, is equal to 41. So First, it says, what is the point estimate of the primary hypertension, pH, patient's total cholesterol mean? So what does that mean? Interesting. So our point estimate equation is going to be x of pH, so our sample mean of our pH minus our sample mean of our NT. Cool. And that will give us 214.71 minus 193.20, and that will equal 21.51. So that is our point estimate. Basically, one sample mean minus the other one. The sample mean of the pH subtracting from the sample mean of the pH, the sample mean of the NT. Okay. Next, it is asking for the standard error of the sample mean of the primary hypertension of the patient's total cholesterol. So, standard of error, basically. Okay, cool. So for our standard of error, our equation is going to be everything under the radical. So it's the square root of everything following of the standard deviation of the pH squared all over the sample size of the pH plus the standard deviation of the NT squared all over the sample size of the NT. That's just kind of, well, that's the formula for this particular scenario. So when you plug all the numbers in, you have 29.66 squared, which again was the standard deviation of the pH all over the sample size of the pH, which is 133, plus 33.04 squared, which was the standard deviation of the NT, all over the sample size of that NT, which was 41. When you compute this, you get 5.765 as your final answer, your standard error of mean. By the way, this was part 2 of question number 2. Next, we are asked to, can you apply the central limit theorem to estimate the population mean of the primary hypertension patient's total cholesterol? Why? Okay. So, the central limit theorem, we have our sample size of pH equals 133 and our sample size of NT equals 41. Essentially, since they're both greater than 30, the theorem applies. Kind of easy enough, I guess. Cool. Let's keep on rolling. Oh God, I'm gonna skip this one. Sorry. Okay, so for the fourth part of question 2, we are asked, find a 90% confidence interval of the population mean of the primary hypertension patient's total cholesterol. Also interpret its meaning. So, confidence level, part D, part 4, whatever. In this situation, we're giving a 90% confidence level according to our standard normal table again, or you can do this using technology. I think it's easier to use the table, more assuring, I guess. The confidence level that confidence level corresponds to a z-score of 1.645. This can also be found by taking your 90% confidence. You subtract your, well, that's also 0.9. You do 1 minus 0.9, and that will give you 0.1. And then to find that z-score, that will be your alpha, 0.1. And then you divide that by 2 to find your z-score. Not your z-score, but you do z sub alpha over 2. Not exactly sure if that's correct grammar. And that'll give you 0.05, and then that will also correspond to that 1.645, if that makes a little more sense. Okay, so to find the interval, that's what it asks for, I believe, right? Yes. Okay. So we do our x, which is again equal to 214.71. That's our sample mean. So we do our sample mean of the pH minus our sample mean of the NT plus our z-score multiplied by the standard of error. And then you do again, that's the first half, that's the second half of the interval. For the first half of the interval, you do the sample mean of the pH minus the sample mean of the NT minus the z-score that we just found, which will be that 1.645 times the standard of error. So to get the beginning of the interval, you subtract the z-score times the standard of error, and to get the second half of the interval, or the higher limit, you add that. So when you plug these numbers in, you get 214.71, which again was the sample mean of the pH, minus 193.2, which again was the sample mean of the NT, plus, I'm sorry, we'll do the lower limit first. So it'll be minus 1.645, which was the z-score that we found that corresponded with a 90% confidence. And you multiply that z-score by 5.765. So one more time to reiterate that, I know that was a little choppy. The lower limit will be 214.71 minus 193.2 minus, in parentheses here, 1.645 times 5.765. And that will give you a value of 12.027, and that will be your lower limit in the interval. For your upper limit in the interval, you will use that same sample mean of 214.71 minus 193.2 plus, in parentheses, the 1.645, which was our corresponding z-score, multiplied by our 5.765, which was our standard of error, and this will give you a value of 30.993. And that will be your upper limit. So your interval will be 12.07 to 30.993. I'm sorry, 12.027. Interpretation, basically, is that this means that we are 90% confident that the difference in population will fall between 12.027 and 30.993. Cool. And on to question number 3. So here it says, a small sample study is conducted involving 15 infants, so I can already see our N is going to be 15, to investigate the association between gestational ages at birth measured in weeks and birth weight. I might have chopped that, who knows, and birth weight Y measured in grams. So our ages our gestational ages at birth will be our X, and our measured in weeks at birth, okay, yeah, and then our birth weight will be our Y measured in grams. Okay, and they give us a table with a bunch of different values. So the first part of this question asks to calculate the Pearson sample correlation coefficient, R, and interpret its meaning. So, and I'm also, you can see here my work. I've written down kind of sentences to kind of guide me along, just to make sure I really touch on where I'm getting all this stuff from. So if you see me looking down on that, that's what I'm doing. Yeah, okay, cool. So using the given table, which gives us gestational age, X, and birth weight, Y, we find that the sum of the X values, so the first thing we do is we find the sum, right? And then we find the mean of the X values, and then we'll do the sum of X minus the mean of X values squared. So, and we'll use all of these again in an equation later on. So the sum of the X values is 575.4. The mean of those X values is 38.36. And then the sum of the X minus the mean of the X squared is going to be 159.176. And of course, our N is 15, which is a given. We do the same thing for Y. Our sum of our Y values is 44,649. Yeah. The mean of our Y values is 2,976.6. And the sum of the Y minus the mean of the Y squared will equal 6,830,289.6. Okay, now we do basically those two sums, the X minus the mean of the X squared, so that 159.176, and we multiply that times our sum of the Y. Not the sum of the Y, but the Y minus the mean of the Y squared. So basically 159 point, Jesus, where am I at? Oh, excuse me. So we do the sum of X minus the mean of the X times Y minus the mean of the Y. There's no squared in there. Yeah, that would have threw it off. I don't know why I was thinking squared. anyways, we get a value of 28,993.46. And moving along. Now, to find R, okay. So remember that 28,993.46, as well as the 159.176 and the 6,830,298.46 that I previously found in the last part of this step to find R. So our equation for R is equal to the sum of x minus the mean of x times y minus the mean of y, all over the square root of the sum of x minus the mean of x squared times y minus the mean of y squared. So you enter all of these numbers in, basically, and you get the values. You plug in the values that I had just told you to remember, which will end up being the 28,993.46 divided by the square root of that 159.176 times that 6,830,298.46. I know it's a lot of numbers, but just try and keep up. Again, you'll see it on my when I scan it in and upload it. But after you compute all of those numbers, you get R is equal to 0.8793. Interpret. So the R value suggests that there is indeed a relationship between the weight of births and the age of the infants. The X and the Y are related. Okay. Part 2 of this question says to test the hypothesis HO, or the null, I believe that's the null hypothesis, correct? Yeah. Test the null hypothesis that P sub XY equals 0 for all the right tail alternative at 5% significant level. Okay. So, just to reiterate, I'm going to give out all the givens, or all the values that we found so far. So we have our null hypothesis is P equals 0. Our alternative is P is greater than 0. Our alpha is 5%, or 0.05. Our R that we just found is 0.8793, and our N is still 15, which was given. So the formula for the test statistic is going to be T equals radical N minus 2, in parentheses, radical N minus 2 times R, divided by radical R minus R squared. So when we plug all of this in, we have T is equal to 13, because remember our N is our 15, and our equation calls for N minus 2. So T is equal to radical 13 times our R, which is 0.8793, which we found earlier, divided by 1 minus R squared. So that will be divided by radical 1 minus 0.8793 squared. One more time, T is equal to radical 13 times 0.8793 divided by radical 1 minus 0.8793 squared. And this will give us a final answer for the test statistic of 6.657. Cool. Now, our degree of freedom is going to be equal to that 13, we got N minus 2, okay? So our degree of freedom is equal to 13, excuse me, my back got tight. So to find our T critical value, we use the table. And according to our table, let me see if I can bring that up real quick. Okay, yeah. So we have our significance level, 13 degrees. We can use the table or technology on this one. I'm not sure exactly what it called for here, but if you're 13 degrees away, you have 13 degrees of freedom, and your significance level of 0.05 given by that alpha, we find that our critical value for T is 2.16. Now, we can conclude that the null hypothesis is to be rejected, since T equals the T that we found with the equation of 6.657 is greater than our critical value of T, which was 2.16. When our value that is found by the equation is greater than our critical value, there's enough evidence to say that the null hypothesis can be rejected. Cool. Oh, we're almost done. Okay, cool. The third part of question number 3 says, fit the line of best fit of y. Wow. Okay. Fit the line of best fit of y on x. Use this model to estimate y when x equals 18 weeks. So we know that our x is equal to 18 weeks, and our formula for best fit line will be y with the caret. Excuse me, I don't know exactly how to refer to that. I'm just gonna call it y with the caret. Y with the caret is equal to a with the caret, plus b with the caret times x. So it's kind of similar to like a y equals mx plus b, but a little bit different. Very different, actually. Scratch that. Okay, so here we don't really have much besides our x. However, we do have an equation for b, which uses our r value. So our equation to find that b with the caret is r minus the standard deviation of y all over the standard deviation of x. And this will give us, when we plug in the values, b is equal to 0.8793, which is the r, times the 674.798, which is the standard deviation of y, divided by the standard deviation of x, which is 3.258. And this, just keep up with where I'm at here on the test. Snapchat. Okay, all right. This b value will then be 182.147. So now that we have b, essentially we have enough variables to solve. So we're gonna solve for a first. So a, when you rearrange things and using a little bit of algebra, when you do the a equals y, you can do a equals y minus bx, derived from the y equals a plus bx. You can rearrange some things and get a is equal to y minus the bx. So we plug in our y, we plug in our b and our x, and we get a is equal to 2,976.6 minus 182.147, which we just found is our b, multiplied by 38.36. Indeed. Okay. Oh, I'm sorry. And then we get a is equal to negative 4,010.57. Let's see where else we gotta go here. We done yet? Not quite, huh? Alrighty then, let's keep going. Oh, crap, we still got to plug in. Okay. Excuse me. So now we plug in all of our values that we have to solve for y. So we have, remember, the y with the caret equals a with the caret minus b with the caret times x. I'm just going to call it y equals a minus bx. And we plug everything in. So we have y minus that a value, which is negative 4,010.57, plus 182.147 times x, which is that 18 weeks that we were given. When we finish this, or when we plug all this in and solve, compute, we get a y is equal to negative 731.92. I believe that should be it. Yes. Yes, okay. Once again, my name is Branden Jackson. Branden M. Jackson, that is me with, a little bit longer hair. But thanks for listening.